Hello students, welcome to EPG Pathshala. I am Professor Devendra Mohan from Department of Physics, Guru Jambheshwar University of Science and Technology, Hisar, Haryana. Today we will be discussing about coupling schemes in continuation to the angular momentum from paper Atomic, Molecular and Laser Spectroscopy. We will be able to learn about the various coupling schemes, angular coupling momentum, angular momentum conservation, spin orbit coupling, LS coupling and JJ coupling, and different types of coupling. Lande interval rule, normal and inverted multiples, determination of spectral terms for LS coupling. Coming to angular momentum coupling, two charged particles, each with a well defined angular momentum, may interact by Coulomb forces, where coupling of the two one particle angular momenta to a total angular momentum is a useful step in the solution of two particle Schrodinger equation. In astronomy, spin orbit coupling reflects the general law of conservation of angular momentum that also holds for celestial systems. The direction of the angular momentum vector is neglected in simple cases. The spin orbit coupling is the ratio between the frequency with which a planet or other celestial body spins about its own axis to that with which it orbits another body. This is commonly known as orbital resonance. Angular momentum conservation. The total angular momentum of a system has a constant magnitude and direction if the system is subjected to no external torque. Angular momentum is considered as a property of a physical system. The system experiences a spherically symmetric potential field. The system moves in isotropic space, and in both the cases the angular momentum operator commutes with the Hamiltonian of the system. Thus the angular momentum and the energy eigenvalue of the Hamiltonian can be measured at the same time by using Heisenberg's uncertainty relation. Examples: let us consider two electrons 1 and 2 in an atom like helium atom. If we consider, if there is no electron-electron interaction but only electron-nucleus interaction, the two electrons can be rotated around the nucleus independently of each other. Nothing happens to their energy. Both operators I1 and I2 are conserved. However, if we switch on the electron-electron interaction, that depends on the distance, of course, d12 between the electrons, then only a simultaneous and equal rotation of the two electrons will leave d12 invariant. In such a case, neither I1 nor I2 is a constant of motion, but the total angular momentum L is equal to I1 plus I2 is considered. Given the eigenstates of I1 and I2, the construction of eigenstates of L, which still is conserved, is the coupling of the angular momenta of electrons 1 and 2. In quantum mechanics, coupling also exists between angular momenta belonging to different Hilbert spaces of a single object, for example, its spin and its orbital angular momentum. If the spin has half integer values such as 1 by 2 for an electron, then the total orbital plus spin angular momentum will also be restricted to half integer values. Reiterating slightly differently from the above, one expands the quantum states of composed systems that is made of subunits like two hydrogen atoms or two electrons in basis sets which are made of tensor products of quantum states which in turn describe the subsystems individually. We assume that the states of these subsystems can be chosen as eigenstates of their angular momentum operators and of their component along any arbitrary z axis. These subsystems are therefore correctly described by a set of L, M quantum numbers. When there is interaction among the subsystems, the total Hamiltonian contains terms that do not commute with the angular operators acting on the subsystems only. However, these terms do commute with the total angular momentum operator. Sometimes one refers to the non-commuting interaction terms in the Hamiltonian as angular momentum coupling terms because they necessitate the angular momentum coupling. Spin orbit coupling. The behavior of atoms and smaller particles is well described by the theory of quantum mechanics, in which each particle has an intrinsic angular momentum called spin and specific configuration of, for example, electrons in an atom are described by a set of quantum numbers. Collections of particles also have angular momenta and corresponding quantum numbers, and under different circumstances the angular momenta of the parts couple in different ways to form the angular momentum of the whole. Angular momentum coupling is a category including some of the ways that subatomic particles can interact with each other. In atomic physics, spin orbit coupling, also known as spin pairing, describes a weak magnetic interaction or coupling of the particle's spin and orbital motion of this particle. For example, the electron spin and its motion around an atomic nucleus. One of its effects is to separate the energy of internal states of the atom, for example, spin aligned and spin anti-aligned, that would otherwise be identical in energy. This interaction is responsible for many of the details of the atomic structure. In the macroscopic world of orbital mechanics, the term spin orbit coupling is sometimes used in the same sense as spin orbital resonance. Hamiltonian of the system depends on kinetic energy of the electrons, potential energy of the electrons due to the interaction between the nucleus and the electrons, and for these two factors Hamiltonian act as unperturbed Hamiltonian. Energy due to interaction between the electrons, spin-spin correlation energy, spin orbit interaction, and for these three factors Hamiltonian act as perturbed Hamiltonian. For lighter elements, the spin orbit interaction energy is much less as compared to the interaction energy between electrons and spin-spin correlation energy, and there will be LS coupling for lighter element, while for heavier elements the spin orbit interaction energy is much greater than interaction energy between electrons and spin-spin correlation energy, and there will be JJ coupling for heavier elements. Coming to LS coupling, in LS coupling it is assumed that when several electrons are present in an atom, each with a definite value of orbital angular momentum Li star and spin angular momentum Si star, such that Li star is equal to Li plus 1 H cross and Si star is equal to Si plus 1 H cross. Due to the domination of interaction energy between the electrons and the orbital angular momentum of the indivisible electrons will interact with each other, and the total orbital angular momentum is given by L is equal to L into L plus 1 H cross, where L varies from L1 plus L2 plus L3 taking the mod of it, minimum to L1 plus L2 plus L3, maximum. The states with different values of L have fairly large energy difference, the state of largest L of being lowest energy. The different levels are designated as S, P, D, F, G and so on, according as L is equal to 0, 1, 2, 3, 4, 5 and so on. Thus, for 3p 4d electrons, L1 is equal to 1, L2 is equal to 2, therefore writing L is equal to L1 minus L2 taking mod of it, L1 minus L2 mod of it plus 1 and up to L1 plus L2, which is equal to 1, 2, 3, giving us a PDF states. For 3p, 4d, 5f electrons, L1 is equal to 1, L2 is equal to 2, L3 is equal to 3. The electrons which are tightly bound to the nucleus will interact first. L is equal to L1 minus L2, L1 minus L2 plus 1, L1 plus L2, again 1, 2, 3, and we get the PDF states. Now L combining with L3 is equal to 3, the capital L is equal to 0, 1, 2, 3, 4, 5, 6 and corresponds to S, P, D, F, G, H, I states. Due to the domination of spin correlation energy, the spin angular momentum of individual electron will interact with each other and the total spin angular momentum is given by S is equal to S plus 1 under the root into H upon 2 pi. The quantum number S can take the values S is equal to S1 plus S2 plus S3 and so on, minimum to S1 plus S2 plus S3 so on to the maximum value. The states with different values of S have considerable energy difference, the state of highest S being of lowest energy. The different levels are designated by their multiplicity 2s plus 1 and thus for one electron S is equal to, this capital S is equal to small s is equal to 1 by 2, so that 2s plus 1 is equal to 2 and we get the doublet level. And for 2 electrons S1 is equal to 1 by 2, S2 is equal to 1 by 2, writing capital S is equal to S1 minus S2, S1 minus S2 plus 1 and up to S1 plus S2 we get 0 and 1 and 2s plus 1 gives us equal to 2 singlet and triplet levels corresponding to S is equal to 0 we get singlet and corresponding to S is equal to 1 we get triplet. For 3 electrons S1 is equal to 1 by 2, S2 is equal to 1 by 2, S3 is equal to 1 by 2 and combining 3 spins we first combine 2 of them to obtain S prime 0 1 and then combine the third S3 is equal to 1 by 2 to each of them. Thus if we couple S3 is equal to 1 by 2 to S prime is equal to 0 we get S is equal to 1 by 2 and if we couple S3 is equal to 1 by 2 to S prime is equal to 1 we get S is equal to 1 by 2 and 3 by 2. Thus for 3 electrons we get the capital S is equal to 1 by 2, 1 by 2, 3 by 2. That means 2 sets of doublets and 1 set of quartets. In the general case of n electrons, the possible values of S are S is equal to 0, 1, 2 up to n by 2 for even values of n and S is equal to 1 by 2, 3 by 2, 5 by 2, n by 2 for odd values of n. The dominant spin-spin correlation and the residual electrostatic interaction having been taken into accounts as a first perturbation, the smaller spins orbit interaction is included in LS coupling as an additional perturbation. As a result of smaller spin orbit magnetic interaction, the resultant orbital angular momentum vector L and the resultant spin angular momentum vector S are less strongly coupled with each other to form a total angular momentum vector J of the atom and J is equal to L plus S. The magnitude of J, L and S remaining constant. The magnitude of J is J into J plus 1 under the root H upon 2 pi, where the quantum number J takes the value J is equal to L minus S plus 1 and so on L minus S. J is integral or half integral according as S is integral or half integral. The number of J values is 2s plus 1 when L is greater than S or 2L plus 1 when S is greater than L. This means that due to spin orbit magnetic interaction, A level characterized by given values of L and S is further broken up into comparative closure 2s plus 1 or 2l plus 1 levels, each characterized by a different J value. The group of these J levels forms a fine structure multiplet. The relative spacing of the fine structure levels within a multiplet is governed by Lande interval rule. Coming to Lande interval rule, under LS coupling, the spin orbit interaction energy is of the form delta E SL is equal to A L dot S, where A is an interaction constant, and let us write J is equal to L plus S. Taking the scalar self product, we have J dot J is equal to L dot L plus S dot S plus 2 L dot S, and J square is equal to L square plus S square plus 2 LS, and LS is equal to half J square minus L square minus S square. So delta E SL is equal to A upon 2 J into J plus 1 minus L plus 1 minus S into S plus 1 H square upon 4 pi square. Now because J is equal to J into J plus 1 H by 2 pi and so on, we can write it as delta E SL is equal to A J into J plus 1 minus L into L plus 1 minus S into S plus 1, where this capital A is another constant, and the various fine structure levels of a Russell-Saunders multiplet have the same values of L and S and differ only in the value of J. Hence, the energy difference between two fine structure levels corresponding to J and J plus 1 is E J plus 1 minus E J is equal to A into J plus 1 J plus 2 minus J into J plus 1, which is equal to 2A J plus 1. Thus, the energy interval spacing between consecutive levels J and J plus 1 of a fine structure multiplet is proportional to J plus 1, that is, to the larger of the two J values involved. This is Lande interval rule. Normal and inverted multiplets. Within a given multiplet, usually the level with smallest J value lies lowest. Such a multiplet is a normal multiplet. There are, however, multiplets in which the largest J value lies lowest. Such multiplets are inverted multiplets, and it is easy to understand how smallest J value lies lowest. The magnetic field B produced by the orbital motion of the electron in the electric field of the nucleus is in the same direction as the orbital angular momentum L. In this field, the most stable state, that is, the state of the lowest energy, must be one in which the spin magnetic moment mu s of the electron lies up in the direction of B. We know that mu s is directed opposite to S because the electron is negatively charged. Thus, in the lowest energy state, L and S are in the opposite direction, and so the value of J is lowest when L and S are in the same direction, which corresponds to highest J. Then mu s is opposite to B and the state is least stable. Determination of spectral terms for LS coupling. Atoms with one optical electron, considering the hydrogen atom or hydrogen like atom, the ground state configuration is 1s, and for this we have S is equal to 1 by 2, L is equal to 0. So capital S is equal to S is equal to 1 by 2, multiplicity 2s plus 1 is equal to 2, and L is equal to 1 is equal to 0, which is S state, and J is equal to L minus S and L plus S is equal to 1 by 2. Thus, a ground state term of hydrogen like atom is written as 2s 1 by 2. The excited state configuration and the corresponding terms for a hydrogen like atom would be 2s, 3s, 4s corresponding to 2s 1 by 2, and 2p, 3p, 4p correspond to 2p 1 by 2, 2p 3 by 2. The ground state configuration for all alkali atoms is 2s 1 by 2. Atoms with two or more non-equivalent optical electrons, 4p, 4d. For this, we have S1 is equal to 1 by 2, S2 is equal to 1 by 2, L1 is equal to 1, L2 is equal to 2. The possible values of S and L are S is equal to S1 minus S2, S1 minus S2 plus 1 and S1 plus S2, which is equal to 0, 1. Multiplicity 2S plus 1 is equal to 1, 3. And L is equal to L1 minus L2, L1 minus L2 plus 1 and L1 plus L2, which is equal to 1, 2, 3 and gives the states P, D, F states. Thus, we have in all 6 terms, 3 singlet terms and 3 triplet terms. These terms can be written as 1P, 1D, 1F, 3P, 3D, 3F. And to take into account spin orbit interaction, let us combine L and S to form J. J is equal to L minus S plus 1, L plus S. For singlet terms, we have S is equal to 0, L is equal to 1, J is equal to 1 and hence we have 1P, 1. S is equal to 0, L is equal to 2, J is equal to 2 and we have 1D, 2. S is equal to 0, L is equal to 3, J is equal to 3, we have 1F3. So, this is for singlet terms. And now coming to triplet terms, we have S1 is equal to 1, L is equal to 1, J is equal to 0, 1, 2, which gives us 3P0, 3P1, 3P2 and S is equal to 1, L is equal to 2, J is equal to 1, 2, 3, we get 3D1, 3D2, 3D3. Similarly, S is equal to 1, L is equal to 3, J is equal to 2, 3, 4, we get 3F2, 3F3, 3F4. This can be visualized in the figure given below, that how we get the S, P, D, F, 3 singlets and 3 triplet terms. So, summarizing what we have learnt is that the process of combining two angular momenta into a resultant angular momentum is called coupling. For one electron, the total angular momentum is obtained in one way by forming the resultant of the spin and orbital angular momentum. A configuration of two electrons with orbital angular momenta L1, L2 and spin angular momenta S1 and S2 allows different ways of arriving at the final resultant of the 4 vectors, which are L1, S1 and L2, S2. The 4 vectors can be combined in pairs in 6 possible ways, as L1, S1, L2, S2, L1, L2, S1, S2, L1, S2 and L2, S1. The last 2 are negligible. However, the spin orbit interaction L1, S1 and L2, S2 are magnetic, while L1, L2, S1, S2 are due to electrostatic force, and the magnetic spin-spin interaction is very small. Thank you.